Hi friends, in this video we are going to see the derivation of Maxwell bridge. Maxwell bridge measures the unknown inductance in terms of a known capacity. So here in this picture you can see the unknown inductance here. So we are going to find out this unknown inductance in terms of a known capacitance in the first term. So that is the basic idea behind Maxwell bridge. So we can see the construction of Maxwell bridge here. Here we have a source. So you can see the symbol because this is an AC bridge. This is having a capacitor and inductor. This will work in AC. So there is an AC source. So in the first term you can see that there is a resistor and capacitor in parallel, and in the fourth term, so here we are denoting it using X. Fourth term we have a resistor and an inductor in series. Now check the second arm, there is a resistor, and the third arm there is another resistor we can see. Now we know the basic equation of bridge balance. That means the impedance of the opposite arms are equal. So here R1 C1 is one arm and Rx Lx is another arm. The impedance of that are equal to the impedance of R2 R3. So let me write the equation of basic bridge balance. So that is Z1 Z4 equal to Z2 Z3. So we can rewrite the equation like Z1 Zx is equal to Z2 Z3. So from this we can find out the equation for Zx. So that is unknown impedance. So Zx is equal to Z2 Z3 by Z1. So we know that Z1 by impedance is equal to admittance. So here we have a term 1 by Z1, so that we can represent using admittance. So we can rewrite like Z2 Z3 Y1. So this is because 1 by Z1 is equal to Y1, and this Y1 is the admittance. So Y1 is the admittance. Now we can substitute each terms. Here Zx. What is Zx? Z is the impedance of the fourth arm. So you can see that there is a resistor and an inductor in series. A resistor and inductor in series. So what is the impedance of that term? So there is a resistor Rx in series with a inductor. So what is the resistance or what is the reactance of an inductor? That is nothing but J omega L. J omega L. So we can see that this is Zx, Rx plus J omega Lx, because this is unknown inductance. So we will call it as Lx. Now we have Z2. What is Z2? Z2 is the impedance of the second arm. We can see that it is purely resistive. So there is only one resistor. So we can write like Z2 is equal to R2. Now Z3. What is Z3? Here also the arm contains only pure resistance. So we can write Z3 is equal to R3. Now the remaining term is Y1. Remaining term is Y1. So that is the admittance of the first term. So this is the first term. So we have to find out the admittance of this term. So here I have given the calculation for the admittance of a parallel combination of two impedances. So here this is a parallel combination of two impedances Z1 and Z2. Then we can write the equation 1 by Zp, where Zp is the parallel impedance. 1 by Zp is equal to 1 by Z1 plus 1 by Z2. So that is nothing but Yp, where Yp is the admittance. So admittance is the reciprocal of impedance. So this is the parallel combination of two impedances. So here what is Y1? We are going to find out what is Y1. So we can see that y1 is nothing but 1 by so there are two components, one resistor and one capacitor. So 1 by impedance of the resistor, that is resistance. So 1 by R1 plus 1 by reactance or resistance offered by the capacitor. What is the reactance of resistance offered by the capacitor? That is 1 by j omega c. So let me correct it and write it clearly. It is 1 by j omega c. So it is the reciprocal of the impedances. That is here we have seen Yp is the sum of reciprocals of the two impedances in the parallel combination. So here 1 by R1. So this is the reciprocal of one resistor, and 1 by j omega c. 1 by j omega c. So this is the reactance of a capacitance. Reactance of a capacitor, and this is the reactance of an inductor. So I hope you remember what is reactance. It is the resistance offered by the inductor and capacitor. So here we have j omega c1, because in this part it is c1. So this is the terms we have. So we have zx, we have z2, we have z3, and we have y1. Now just substitute these terms into this equation. Just substitute these terms into the equation of zx. We can find out the value of the unknown integral. So this is the equation where we are going to substitute these terms. So let me scroll down. So zx is equal to z2, z3, y1. So that is the equation. So z2 is r2 and z3 is r3 and y1 is 1 by r1 plus, we know that 1 by j omega is nothing but j omega c, because it will go to the numerator. So zx is nothing but rx plus j omega lx. So we can write it like rx plus j omega lx is equal to r2 r3 by r1. So what I have done, I have just multiplied it inside. Okay, I am just taking the terms inside. So that is rx plus j omega lx is equal to r2 r3 by r1 plus r2 r3 into j omega c. So now we can see in this kind of situation, this is a complex term. It contains a real part and an imaginary part. So here also this RHS also contain a real part and an imaginary part. So in this condition, in this situation, we can equate the real part and imaginary. We have already seen in mathematics that we can equate the real part and imaginary part. So if we are equating the real part, we can get Rx is equal to R2 R3 by R1. So we are just equating the terms which do not contains any imaginary terms. So Rx is equal to R2 R3 by R1. Similarly, we can find out j omega Lx is equal to R2 R3 j omega C1. So here it is C1. Now we can just see that we can cancel the j omega terms from both the sides. We can cancel the j omega terms from both sides. So the remaining term is Lx is equal to R2 R3 C1. So these are the two terms remaining at the end. So these are Rx. Rx is nothing but the unknown resistance in the part in the fourth amp, and Lx is the unknown inductance in the fourth branch. So you can see that Lx is R2 R3 C1. So in the beginning itself I said we are going to find out Lx in terms of a non-capacitance. So the unknown inductance in terms of a non-capacitance. So that is the basic idea behind Maxwell bridge. The inductance, okay, the inductance, not just inductance, it is unknown inductance. So the unknown inductance in terms of a non-capacitance. So here the non-capacitance is C1. So using C1, R2, R3 we can find out the unknown inductance value. So you may have a doubt why I am using this term Y1 here. Y1 here instead of why can't I use like this Z2 Z3 Z2 Z3 by Z1? Why can't I directly find out Z from this branch, one from this branch? So let me try to explain what is the reason. For example, if you want to find out Zp from this equation, that is just we have to take the LCM. So Z2 Z1 plus Z1 plus Z2. So that is the effective impedance of a parallel combination. So you can see that this terms already contain, this arm already contain a capacitor, and the reactance of the capacitance is 1 by j omega c. 1 by j omega c. So if we are doing the calculation in this method, the calculation will be a little more complicated. So to avoid the complication, I am taking Yp instead of Zp. So I am taking Yp instead of Zp. So Yp is simple. So that is just 1 by Z1 plus 1 by Z. That means just add the reciprocals of the impedances. So take the reciprocal of the impedances and just add it, you will get Yp. So to make the calculation easier, I am taking Zp. There is Yp. There is nothing more than that.